lockdown.
I see.
So we have some COVID cases. So we just got the circulars and there's a bit of a confusion across.
Shomak, Pune is in a bad state, right? I mean, almost like Delhi.
Very bad state. And I just saw Delhi went into a lockdown from tonight, right? Pune is refusing to do that because there is so much pressure from industry. Pune should have locked down a long time ago. And now it is in a very bad shape.
Yeah.
No hospital.
Here there was one which could happen. In Chandni Chowk, traders got together and said that they will voluntarily go into a lockdown.
See, this is the difference. Yeah. Chandni Chowk can do it, Pune can do it too. But Pune just has they call it a lockdown, but it's a curfew. And of course, you can't do, I mean, nobody in Pune wears a helmet.
Yeah.
And so,
they in the rest of the world, they wear helmet to save the head. Here they wear helmet to save 100 rupees.
What can I say? So I'm just wondering, should we wait for a minute or should we start? Because
it's okay. I mean,
I can't find my head of the department. So.
I mean, it's all right, Madhuri. Just start. You don't need anybody else.
Yeah, I think so.
We're here.
Yeah. So let me just start off so that we can wind up on time, and anyway they'll be joining us. So welcome all of you to this inaugural function for VINN, our Astronomy and Astrophysics Club of CUTN, and my profound thanks to both Professor Shomak Chaudhary and to Professor Sheshadri. And I'll just make a brief presentation about the genesis of, why we are here today, from where we have come, and that will tell you why I'm so thankful. So just let me share my screen. So let me just go to this.
Yeah, you can see it.
Yeah, you can. That's right. Yeah, I'm just trying to find the. Sorry about this. Give me a second, and there we go. So yeah. Again, once again, warm welcome to each of you to this inaugural function. This is our department logo to the right, which was designed by our students long time back to represent not only the physics department at CUTN, but also the famous Tiruvarur chariot of the Ratha, which is extremely famous. So, so they came up with this, and one of the two people who designed this was Ruchi.
You're muted. You got muted.
Yeah, sorry, somebody muted me. I don't know who did that, but yeah. So a quick overview of where we started and where we are here. It all started with a visit from Shesh, to give a talk long back in 2014. And he spoke something about the history of universe, and this was a public lecture, a colloquial kind of a talk. Now, between 2014 and 2018, we had been talking a lot about how the students were interested in astronomy and astrophysics, but we didn't have resources to support their enthusiasm because none of the faculty are trained, and we don't. Somebody is constantly muting me. I mean, whoever is doing this, please be careful not to. I don't know who it is, but one of the co-hosts, please be careful. So after a long discussion and with help with Shesh, we formulated an elective course, which was called the Physical Principles Governing Astrophysical Process, because I didn't want to be over enthusiastic in starting something which I could not handle, but we wanted it within the department. So between NPTEL talks and me, we started this elective, which has had a tremendous support from the students. They, every time we offer, we have students taking it. Until last year, I was teaching, and now we have a faculty who teaches. And from 2018 onwards, we have had student internships happening all across the country, and including, in particular, Indian Institute of Astrophysics, IUCAA, DAFR, ARIES, so on and so forth. And also MSc projects, which was semester-long projects that were guided both individually by faculty here and in collaboration. And of course, Professor Raj Chaudhary himself is one of those collaborators. In 2019, I conducted a university level quiz on astronomy and astrophysics just to keep the momentum going and ensure that students were still there with us. And after this, 2019, 2020, we have had tremendous support from IUCAA. We have had 2 workshops fully funded by IUCAA run here. And the response has been overwhelming in the sense that I think we had to take about 1.7 times the number of students that we expected, participants that we expected. And that led to also a faculty recruitment in 2020. Dr. Sampurnanand has joined us, and he's trained in, he specializes in astrophysics. And in the last few months, we have had 3 talks by Prajwal Shastri, Soumya Jana, and Sheshadri. And all this as the background, our students wanted to start this club during the COVID period, saying that they are very enthusiastic about hearing more and more about the topic, and here we are. So this is the brief history of what we have been trying to do here with reference to astronomy and astrophysics. So a quick overview, just to give you a glimpse. This was the first IUCAA CUTN school on astronomy and astrophysics, which is very at a fundamental level. IUCAA Associates, Tia Sheshadri, Joe Jacob, and Arunima Banerjee had conducted this. And what was interesting about this was our then Vice Chancellor, and you can see the crowd that was there. What was interesting about these is that in addition to being a training ground, it also created an atmosphere of, just an academic atmosphere which was much lacking before. So sitting at the cafeterias and discussing physics, and at nights. In fact, in the second workshop, I think the students were working till 10:30 at night, which was unheard of here. So these workshops actually set a certain tone for academics and the interactions between faculty and students. And this was the second school, which was run last year with Shesh, of course, and Sriram Kumar, H.S. Mani, Dawood Kothawala, with Sampurnanand and Ramkishore being our TAs, and Sampurnanand eventually joined us as a faculty, and he's our colleague. So here again, you can see the major enthusiasm, and the photographs speak of, volumes. And the constant tutorials. The tutorials again are things that these workshops were famous for. Of course, you can see typically Shesh using the walls in the cafeteria to teach. And so this was a great moment for all of us, watching this happen. It actually sets a certain tone for the entire, atmosphere. I mean, this is something we are absolutely grateful. So, just as a brief overview, these were the projects that have been guided in the areas of astronomy and astrophysics. I work with astrochemistry, my colleague on statistical physics, and of course, Professor Chaudhary has guided, co-guided Lakshmi. Malvika Uni has been there, and this is our current student. In fact, Rohan and Hakim are currently pursuing. And we have had these 3 talks this year, which is, Prajwal spoke to us for the Science Day, Women's Day combination. So she was speaking about discovering black holes in ungendered physics. And we had the other 2 talks as a part of our national seminar that we were running. So yes, this is a summary of it. CUTN plus support from other agencies, and initial students who were, the brave hearts who walked into this field, not having adequate support here, but willing to take this. And we are starting this club today. We plan on having a series of introductory level lectures in astrophysics to be delivered by experts, so that it helps the students to understand the fundamentals. And also hope to go in for some popularization events, because the moment we announced this club, we had requests from school children who said that we want to join and we want to learn. So, I mean, I really hope that COTN, our students and others are a nodal center where we can do something to keep this enthusiasm going.
Also,
looking forward to,
these local students, it's a very unique opportunity
yes,
for them, local school students. Otherwise, they would not have had it.
Absolutely, absolutely. Absolutely. I mean, in this area, we don't have anything else, to support them. And we are in a very rural setting. So we are the only university in this district, and we have our own unique points. So uh, they constantly, I mean, I'm looking forward personally to your constant support both from CUTN and from Ayuka. I hope you sponsor summer workshops because these have really taken our students a long way. And that is the reason why I said a big thanks to both Shesh and to Ayuka. Thank you for being so supportive and bringing this entire department to a position where we are able to satisfy us at least a certain curiosity of the students. So thank you so much. Now I invite our head of the department, Professor L. Kavika, to say something about the department and give her introduction.
Good evening to all. So I feel privileged to invite our officiating Vice Chancellor, Professor Kumarvel, and Professor Somak Rai Chaudhary, the distinguished speaker and most valued speaker of today's event, the Director, Inter-University Consortium for Astrophysics and Astronomy, Ayuka Pune, and Professor T.R. Sheshatri from University of Delhi. Professor Nagarajan, the Controller of Examination, the Dean of our School of Basic and Applied Sciences, professors, colleagues, research scholars, and students. I am very glad to invite you all to this official inauguration of long pending and highly anticipated VINN, meaning Sky in Tamil, the Astronomy and Astrophysics Club of our Department of Physics. So though it is a second club of our department, in addition to the Perturbations Club that we already have, I believe this Astronomy Club will be a hit among our students. So especially not only with physics students, so more fascinated by our mathematics and other core sister departments. On this special eve, on behalf of the department, so let me congratulate the faculty coordinator, Professor Madhurima, for her efforts, and I record my sincere thanks to the director, Professor Somak Ayuka, for having joined with us in this great initiative. So my special thanks to Professor T.R. Sheshatri, who has been the driving force, not only for this academic activity, he has been supporting us in many more academic programs, and his face is more familiar, rather our faculty in our student community.
Thank you.
So this Astronomy Club is a great way to keep our students engaged with the activities, which is entirely different from our daily routine studies and gives a chance to connect the earth and sky through stargazing together. So the knowledge and the information in this field of astronomy is so vast that everybody knows, and there is no dearth of how much one can learn in this field. So this club VINN is paving a delightful way to connect with peers and to explore playfully the celestial bodies, sun, moon, solar system, faraway galaxies, the extraterrestrial, and there is so much to learn. So our department is actually offering a 5-year integrated master's program in physics. A student who joins in his first year of this academic journey with this Astro Club VINN, I surely say that they will learn this field in a playful way without any strain or brainstorming sessions, and will learn this field in a hobby mode, and this will really help them to set their career in this field. So as Professor already have pointed out, Lakshmi Tulasidaran is one of our best students, and Ayuka has played a major role in setting her career. So not only her, many more students we will expect in future. So with these few words, once again, I thank our officiating Vice Chancellor who has joined us and for sparing his valuable time with us to inaugurate and declare open this club VINN. So I wish you all the best. I wish all the students, and I hope we have many more exciting stargazing and night watching skies ahead. Thank you very much.
Thank you.
Thank you, Professor Kavita. Is Professor Nagarajan around?
He will be joining, madam. He is facing some difficulty in joining.
Okay, fine. In which case, I would now request our officiating Vice Chancellor, Professor Karpakukumaravel, from the Department of Education and our officiating Vice Chancellor right now to give his opening remarks and for the inaugural event. So kindly unmute yourself. Yeah.
Audible to you?
Yes.
Okay. So good evening to all of you. I would like to congratulate the Department of Physics and Professor Madhurima and Professor Kavita and the team of faculty in the Department of Physics in particular for promoting astronomy and astrophysics in collaboration with Inter-University Center for Astronomy and Astrophysics at Pune, whose director has graciously agreed to inaugurate this significant event. I am very glad that the Inter-University Center for Astronomy and Astrophysics has provided an associateship to our Professor Madhurima, and I am thankful to Professor Somak Rai Chaudhary, the director, who himself has supervised some of the projects of our students in CUPS. I am also thankful to Professor T.R. Seshadri, Professor of Physics at Delhi University, for his initiative and support. And I am very happy that with all your support and encouragement, under your able guidance, the students of CUTN have started an astronomy club. And I am very glad to record my appreciation to the committed faculty and the motivated students and the enlightened dignitaries and resource persons who have contributed in successfully organizing this very significant event. As an educationist, I would like to just show my curiosity of why we should teach astronomy. I think it should have its taking in the school level itself. Such a very interesting subject, a very vital subject. I feel that it is not getting its due attention at the school level. Such an interdisciplinary concept which brings cultures together and inspires arts and beauty. This astronomy is very useful as it rises us above ourselves. And it shows how small we are, how great our mind is, how our intelligence can embrace the whole of this dazzling immensity. Exciting, fascinating, multidisciplinary. This astronomy, I should say, is an amalgamation of various disciplines like mathematics, physics, humanities, history, arts, religion, and philosophy. For physics, astronomy is used to illustrate many concepts of physics such as gravity, light, and light spectra. In mathematics, historically there has been a lot of mathematical development through astronomy such as trigonometry, logarithms, and calculus, and hence astronomy can be used to illustrate those branches in mathematics. Geology, Astronomy has advanced the geological sciences by providing a variety of environments of other planets and moons. History in scientific revolutions, astronomy stands out. Astronomy has historically contributed to many practical applications. Philosophy. Astronomy reveals philosophically our cosmic root and our cosmic place in space and times. It asks the most fundamental questions. What is the origin of the universe? Galaxies, stars, planets, atoms, the molecules of life. What is the origin of us? And what is the relationship between an individual and the universe? So that way, it has international connotations. It brings different subjects together, different cultures together, different times together, different borders together, and it requires data from different latitudes and longitudes and foster international collaboration. So that way, such a vital subject, I am very happy that it is taking its roots in the Central University of Tamil Nadu through the initiatives of our Professor Madhurima under the headship of Professor Kavida. And once again, I would like to all the dignitaries, all the resource persons, all the experts for graciously honoring our invitation and making this event a very significant one. And I wish that such a tempo, such activities should gain momentum in the months to come, in the years to come. And after the COVID-19 pandemic crisis is over, I take this opportunity to invite Professor Somak Rajchaudhary, Professor T.R. Seshadri, and all the other dignitaries here to come to CUTN in person and have your physical presence to interact with our scholars and students. Once again, I am very happy to deliver my presidential address, and I once again record my appreciation for the organizers in organizing such a relevant program at a very right time. I wish the event all success. Thank you very much.
Thank you.
Thank you very much. Thank you. He has just come back from a tour and he wasn't sure if he could join us. So thank you very much for taking the time to join. And I think the Dean of the school is unable to join for some technical reason. So now I would request our students to share their expectations and their experiences in this, starting with three of them said that they would be sharing their opinion. So Devika, Alan, Sunny, and Malvika. So I think you should go. I invite the students to share their. Devika, who's starting? Devika, Malvika, or Alan? Any one of you?
Ma'am, I shall take up. Devika was supposed to talk first.
It's okay, but if there's an issue, you can. Why don't you start your video and yeah.
Okay. Good evening, one and all. The primary goal of the club is to impart basics of astronomy to its members and to foster their interest. Since we are a community having a variety of academic backgrounds, our activities and programs shall try to accommodate the diversities. We wish to conduct monthly discussions on chosen topics. Everyone is free to ask your doubts and queries related to astronomy in the VINN Google Group Forum, which will be discussed in special doubt clearance sessions. We'll also have some sessions where every individual participant is encouraged to come up with their own thought experiments and ideas to solve mentally stimulating astronomy, astrophysics problems. There will be also events like quizzes and webinars. We are always open to your suggestions, so please do write to us. Please share with us your opinions and ideas. Now, I call upon Alan Sunny to give his talk. Thank you.
Good afternoon, everyone. VINN is actually a dream come true for all of us. An idea that slowly took its form and now it became a realization for us. I want to thank our mentors on behalf of the student members of this club. Respected Madhurima ma'am, you inspired us and helped us in each and every step in making this dream of ours a reality. I'm proud to say that the name of our club, VINN, was coined by ma'am herself. Thank you so much, ma'am, for your leadership. Sambhoon sir mentored us, and his immense knowledge in the field of astrophysics helped us all during the formation of this club. Thank you so much, sir. I would like to take this moment to express our heartfelt gratitude to our respected head of the department, Kavita ma'am, who is the driving force behind the entire academic activities of the department and the formation of this club. Finally, it's my privilege to thank the dignitaries, esteemed speakers, respected faculty members, and the students of the Department of Physics. A huge mention to Vaishnavi from first year who designed this amazing logo for our club. Carl Sagan, a man who inspired a generation of astronomers, said, "We began as wanderers and we are wanderers still." Yes, each and every one of us is an explorer and we are ready to set sail for the stars. Let us take this journey together, exploring other planets, stars, and galaxies, wandering in the vastness of the universe. Let us ask questions, look into the amazing and puzzling celestial phenomena. Who knows, we may end up finding some amazing answers. We believe that this club will help in nurturing the astronomer inside everyone and inspire many students to take the path of astrophysics. Let me quote Sir Stephen Hawking: "Look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious." Thank you. I welcome upon Devika to...
Devika, are you in a position to speak now?
Hello, ma'am. Am I audible?
You are, yeah.
Okay, ma'am.
Yeah, I think you should go ahead. Yeah.
Yeah. So, greetings to all the dignitaries, professors, and dearest members of the VINN Astronomy Club. VINN is the realization of a long dream. The aspiration to set up this club is as old as UTN itself. The students of our physics department have always shown great interest in astronomy. Their enthusiasm, along with the support of professors, has led to many events in the Department of Physics, like IUCA's UTN School on General Relativity and Cosmology in 2020, Introductory School on Astronomy in 2019, etc. The motivation for this club is the interest and curiosity shown by CUTNites in the field of astronomy and astrophysics. There is an astronomer in each one of us. We have been looking at the night sky for so long, wondering about celestial objects, their origins, and the numerous mysteries of the universe. We have been in a long search of a community where we can share our curiosities and doubts that pestered us whenever we looked at the night sky, and discuss the astounding facts we have learned about the universe through the course of time. And today, that community is realized. This club is not just aimed at physics students, but for all those curious minds who wonder about the universe. Through this club, we wish to eradicate false information and myths regarding astronomy and to establish facts about the universe in the minds of students. I thank all the teachers, professors, students, and all my winner members for making this club a realization. Thank you. Thank you so much.
Thank you, Devika. Thank you very much for sharing your thoughts. Now the floor is all yours, Professor Shumak and Shish. Your comments, your talk, we are looking forward to that. Professor Shamak, I think you'll be starting, right?
No, I think let Shashank go forward. Thank you very much. I'll follow it.
Hi everyone, it is great to be interacting with CUTN, and as Madhurima was mentioning, I have always enjoyed interacting with your group, a bunch of very enthusiastic students, and they are often in touch with me much afterwards also, and every day I have some kind of message in WhatsApp or something asking doubts and so on. Okay, so let me just share my screen. Can you see it? Yeah, just still coming up. Yeah.
Come up.
Okay. So
maybe
black holes, something.
Full
yes,
screen
Madhurima?
mode is the full screen mode.
Okay, I'm doing it from my laptop, so I don't know.
That's fine. That's fine.
Okay.
That's fine.
Not laptop. I'm on my iPad, so I don't know. Okay. Yeah. So black holes are something which is a kind of a curiosity with a variety of people. You see, often you give a talk about anything in astrophysics, gradually it will drift towards the end about what is a black hole, and it is not without reason. Black holes, as I have said in this slide, are most enigmatic, that the theoretical understanding is very intricate, and the theoretical model behind it, and also as far as their observation is concerned, have been extremely elusive in the sense that black holes are something like ghosts. In a ghost movie, you will see the door opening, you see the signature of a ghost, but you don't see the ghost. So often black holes are like this. You see its signature through gravity, although it's very difficult to see it directly, and more about it will be talked by Shamak. What I will discuss is the history of the theoretical basis of how these black holes were, people try to understand this. So first of all, long ago, we had Newtonian gravity, and then we had Coulomb's electrostatics. And let us make a comparison between these two in order to understand the gist of the theories which led to the suggestion of a black hole. The Newton's second law basically says that force is proportional to acceleration, and proportional constant is called mass, which is a measure of the inertia of the system to resist motion. Now, this was Newton's second law. Now, Newton also propounded a theory of gravity in which he said that force of gravity is inversely proportional to the square of the distance between particles, and importantly, he said it is proportional to the mass of the body on which the force is felt. Now, using this second law, if we put these two together, we get acceleration of the body is equal to minus gm by r square into m prime by m. I have purposely written one mass as m prime and the other as m. Now, offhand, there is no reason why they should be the same. In fact, technically, m prime is called the gravitational mass and m is called the inertial mass. However, Newton postulated that m prime and m are the same, and this was motivated by observation. Now, there is no a priori reason why they should be same. It is an observed fact. And all experiments to detect the difference between them have failed. And the upshot of this is that if m prime is equal to m, then the acceleration is independent of the kinematic parameters of the particle, which means whether I have a small stone or a big rock, it will behave in the same way in a given gravitational field. And in fact, this is very important. We must have seen astronauts coming out of their spacecraft, doing a spacewalk and getting in. If the trajectory of the particles were to depend on the mass of the particles, the astronaut would go one way and the rocket would go the other way. The fact that this spacewalk is possible and the astronaut can safely get in is because the trajectory of the particle under gravity is independent of the mass of the particle. Now we can contrast this to Coulomb's electrostatics. In Coulomb's electrostatics, we have force proportional to, again, 1 by r square, but it is proportional to q. And if we take Newton's second law, we have an acceleration proportional to the charge by mass. And hence these don't cancel out. Hence acceleration due to electrostatics depends on the kinematic details of the particles, whereas in pure gravity, it does not. Now, this is a very important basis on which Einstein set up his general theory of relativity. What it says is that if suppose the trajectory of the particles do not depend on the kinematic parameters of the particle, it means that the trajectory of the particle can be attributed to a change in the nature of geometry. And this is how Newton made a geometric theory of gravity. But before we come to that, let us see how did other people before Einstein try to use Newtonian gravity in the context of what we are talking about. Now, given a spherically symmetric body, now a particle, if you project it radially away from the symmetric body with an escape velocity, with the velocity v escape, then it means that the particle will never return. Now, so you have half mv escape square, which is the kinetic energy at escape velocity, is equal to the potential energy. And this is the condition for v to be the escape velocity. And we get escape velocity as 2 gm by r. Now, Laplace asked a very interesting question. He said, okay, suppose the escape velocity is the velocity of light. What is the radius at which the particle should be projected? And that happens to be Rs, which happens to be equal to 2 gm by c square. And if at this radius, even light cannot escape the gravitational pull. Remember that the special theory of relativity was still far, far away. It happened only in 1905, which I'll come to. But Laplace committed 2 errors. But both these errors cancelled out, and as you will see, that is why he got the right result. One is that energy of light is not half mv square. Okay, it is only for non-relativistic matter. And secondly, Newton's law of gravity is not valid in such strong gravity. However, we can't blame Laplace because at that time, these things were not known. And these 2 mistakes cancelled out to give the right result. Then came the years 1905 to 1950. In 1905, the special theory of relativity was formulated by Einstein, according to which nothing can travel and accelerate past the speed of light. Now, this was important because Laplace just said that if it is the speed of light, what will happen? He did not rule out the possibility that something can move faster than light. But this put a bound on how fast it can move. And this special relativity was a description of space-time without evoking gravity, but for free space. Now, in 10 years later, Einstein managed to marry relativity and gravity together to come up with the general theory of relativity. And it is the general theory of relativity which relied on the fact that the trajectory of the particle is independent of the kinematic parameters, and that led to the geometric theory of gravity, which Einstein propounded. So in pure gravity, all particles behave in the same way, and that is how this was possible. Now, clearly, since Newton's law of gravity is seen to be correct in day-to-day situations, Einstein's gravity and Newtonian gravity in the weak gravity limit are almost indistinguishable. But when you have strong gravity, they part ways. And that is why in strong gravitating systems like a collapsed star, these things show up very easily. The very next year, that is 1916, there was a person called Karl Schwarzschild who was a soldier in the First World War for Germans. And it is said that when he was injured and he was in his deathbed in the hospital, he actually worked out a solution, the first exact solution for Einstein's theory of gravity, which later was to become the black hole. So this theoretical prediction was one in which he predicted an object from which even light cannot escape. Same what Laplace said, but it was on more rigorous footing. And later, Wheeler gave the name black hole for such things. What was different from Laplace calculation? As I had said, Laplace calculation was two wrongs making it right. Now, there are many other predictions of Einstein's theory of gravity, and they are all realizable in strong gravity. Now, the theoretical predictions are, for example, modification of trajectories of particles. Now, according to Newtonian gravity, the particle trajectories are ellipses in general. Now, according to Einstein gravity, they are modifications to this. For example, you can have the ellipse not only the particle going around an ellipse, but the ellipse itself precessing around the center. The other interesting observation, which was done in 1919, was the deflection of light. And what this says is that just like ordinary matter, even light gets deflected in a gravitational field. But there is a small difference. There is a factor of 2. If you use Newtonian gravity, you will get an answer. And if you use Einstein gravity, you will get a factor of 2. And that comes up in the presence of strong gravitational field. And that is where they part is. And you can have a situation in the vicinity of a black hole such that the light gets bent so much that it goes in a circular orbit around the black hole, or what is usually said, you can see the back of one's own head. Now, direct observations were almost impossible for black hole till recently. Recently, there has been very interesting experiments done, observations made, and this had led to the recent Nobel Prize for this. And I now hand it over to Shomak Rai Chaudhary, who will enlighten us on this further. Thank you.
Thank you very much. Thank you very much, Professor Sheshadri. And before that, I would like very much to thank the people who introduced this concept. Professor Madhurima for starting this club, which I think is absolutely fantastic. And thank you very much for the welcome that was given by Professor Kavita HOD and also Professor Kumar Ravel, the officiating Vice Chancellor. It just makes this occasion very special. And from my point of view, I can say that I have been looking at CUTN for a long time. As I said, as was said, I've supervised students from here. And I've been always very keen for astrophysics to start as a subject at CUTN. As an educational subject, and I completely agree with the Vice Chancellor when he said that astrophysics is a subject that should start from basic school level, and this is something we are trying to do quite a lot from IUCA. As you probably know that the International Astronomical Union has set up the Office of Astronomy Education to start all over the world astronomy to be taught at the school level. And we have been selected as one of the offices of the 5 offices that will be set up worldwide to figure out how this will be done all over the world. So this is something that I'm very excited about. And in particular within India, our job is to make sure universities, particularly central universities like CUTN, teach astronomy. And I'm very happy that this is happening. I haven't been able to come yet. There was a problem when you had the IUCA workshop, but I will certainly make it a point to come as soon as this is possible. And I can assure you that IUCA will support astronomy in whatever form at CUTN. Absolutely. And personally, I will absolutely see this. Having said that, let me continue the story of black holes. So I think that was an excellent introduction by Professor Shadri about where this concept came from. And so I'm going to share my screen, and I'm going to talk about astrophysically how you actually see these things. So let me share my screen and see whether we can you see it now? Let me see if I can.
Yes.
Yeah. Okay. So my idea is to see how to find these things. So just to continue from the previous talk, as you know, we know Newton, and Newton's idea was gravity is a force, but Einstein changed all that. Einstein said, no, let's think about gravity in a more general sense, and the general sense turns out to be including the results of Newton, but also to look at what happens to things that move close to the speed of light, as well as things that have a lot of gravity. And it turns out that Newton's laws were not enough to support these extreme cases. And so the idea was then we know that gravity is not a force, as was said, and essentially it is space-time itself that's bent as a result of the effect of the mass. And for example, here is a lovely graphic that shows, for example, that around the sun itself, space itself is curved, and the Earth follows the trajectory that it does, according to Einstein, because it follows the easiest path that it can follow in this curved space-time. And that is the concept that Einstein taught us to think of gravity as. And as a result, what happens is that if you can think of the Earth moving around the sun, and that causes a warp in space-time, then a black hole is an object, as Schwarzschild described, as Shazli said, just within a year of Einstein formulating this idea of space-time, such that the warp of space-time is so extreme that nothing can come out of it, not even light. So how big is this black hole, and how dense does it need to be? Here's the Schwarzschild radius, the formulation of Schwarzschild radius, and it says that what happens is that it's so compact that the escape velocity exceeds the speed of light, and so nothing can come out of that extreme warp of space-time. And if you look at actual quantities, you can see that anything, because it's a formula that has a mass in it, and that's it. And you can see that the speed of light is so extreme, you put it in there, it means that the Schwarzschild radius itself has a value that's very, very small. So I can turn you into a black hole. By putting your mass in there, you can figure out what that size of that black hole would be. Anything can be turned into a black hole if you have a physical process that can convert that object in it. And so for the Earth to turn into a black hole, it has to be smaller than a centimeter in radius, and that you can't think of anything that can do that, thankfully. But you can. And so you can work out from this particular formula, just scaling how you can be turned into a black hole, what your size needs to be. And there's mercifully nothing that can compress you to that kind of a radius. For the sun, that radius is about 3 kilometers. And as you will see, that becomes possible. So here's one thing about a black hole, that black holes are not going around the galaxy trying to suck everything in, as is often seen in science fiction and science fiction movies. So a lot of people wake up in the middle of the night afraid that they're going to get sucked into a black hole. You won't. In fact, even if the sun becomes a black hole tomorrow, it won't. But if it does, then its power is not strong enough to pull the Earth into it. The Earth will go around the sun as if nothing happened. Of course, we won't get any light, and of course we'll all die because there'll be no light. It'll be a very dark place. But it's not going to fall in, and that's what you see in a lot of science fiction movies. They, things turn into black holes, stars turn into black holes. They pull everything in, and that's not going to happen. They are the effect of a black hole of pulling things in actually stretches not to scales as large as the solar system. Okay. So having said that, let's think about how to find these beasts. They are very difficult to find because, as you know, a black hole does not let out anything. And so we see things in the universe from the radiation they emit. And so if nothing can come out of a black hole, technically you can't see them. It's just dark, it's black. And so how will you see them? So we know that there are at least two kinds of black holes in the universe. There are these stellar mass black holes, which are a few times the mass of the sun. I'll tell you in a minute what that means. But these black holes are masses that are like stars. There are also these supermassive black holes, which have 10 to the power 6 to 10 to the power 9 times the mass of the sun, and they reside in the centers of galaxies. Each big galaxy has a supermassive black hole in the middle. And we know that, and you will see that, of course, our galaxy also has one, and because it's a big galaxy. Now, then people have asked for a long time, are there any ones in between? So are there, for example, black holes that are 10,000 times or 5,000 times the mass of a star, and we have never found them. And so there's always been a controversy. Are these there? Are there? And if, for example, you form these supermassive black holes by merging together small black holes, you should be able to find things in between. And as you will see towards the end of today's my talk, we've actually started very tantalizing to find these things. So and it's very, very interesting that there might be mid-mass or intermediate mass black holes, right? So here, let's look at what the supermassive black hole looks like. So here's, as you know, we live in a galaxy called the Milky Way. This is what the Milky Way looks like. If you look at the top view, it has these 5 spiral arms, and this is what the stars look like. And if you look at it from sideways, of course, this is not a picture. You can't take a picture of our galaxy by being inside it. This is an artist's impression, but you can take pictures of other galaxies which look like our galaxy, and they look very much like this. Is a flat disk with a bulge in the middle. This very much looks like a chapati, which is kind of has a bulge in the middle. And the sun, along with the Earth, is not at the middle of the galaxy. It's about 8 kiloparsecs, which is 20,000 light years, 25,000 light years, offset from the center, right? And so when we look at the sky, we look at the stars, we actually are looking through this thin screen of stars, and we're looking at the sky like that, okay? And most of the time, all the stars that we see in the sky with the naked eye are actually the stars that are in this thin layer in the disk where we are, except when we look towards the center of our galaxy, and then we see a big kind of a river of stars, and that is why it's called Akash Ganga, right? Or Milky Way, as if lots of milk is being thrown around the sky, right? And that's what the Milky Way looks like. And so what we're doing here is that, as I said, all major galaxies have a supermassive black hole in the middle. So right in the middle here is the supermassive black hole. And we have a supermassive black hole in there. And the question is, how will we be able to see it? One of the things you can see is that it's got this amazing amount of dust in the disk of the galaxy, right? You can see there's black stuff, and that's dust that did not get into the stars, dust that came out of the stars as they were processed and exploded. And so this fills the plane of the galaxy, and we are in the plane of the galaxy looking towards the center to find this black hole. So there's a big challenge there, that we have to see through all that dust. So light has to come through it, right? And one of the ways we can see the black hole, we can't of course see it, is to try and infer the size and mass of the black hole by looking at the dynamics of stars around them, right? And you can do that, for example, in the solar system. You can measure the mass of the sun by looking at the orbits of the planets around the sun. If you just take the orbit of the planet, you can measure the velocity of the orbit, the size of the orbit, etc., etc. You can find out what the mass of the sun is. Similarly, if you can take stars that are very close to the central object, even if you don't see the central object, you can figure out its mass and its size. So here you are. We know that the star cluster in the center of the Milky Way is called Sagittarius. Sagittarius A star is the name of this black hole, which is, of course, you can't see. But there's a star cluster that's around it. And the idea is that if you go very close and find out the stars that are extremely close to the black hole and find their motion, then you can figure out what the black hole is like. So this is the idea. So you have these stars and they're going all around. So this was taken up by two groups, one of them using the Keck telescope in Hawaii, which is the largest telescope in the world right now, 10-meter telescope. And as you can see, if you go inside, there is 72 separate mirrors making up the 10-meter. You can't build a 10-meter mirror. There are 72 hexagonal mirrors that make up the mirror, right? And the interesting thing is that this mirror is built such a way that the mirror itself can change its shape in real time. And as a result, it can help focus and increase the resolution of the mirror in an unprecedented way. This is called adaptive optics. So one of the problems we have in going very close to the black hole is that you really have to look at the stars that are really close to the black hole. Otherwise, as I said, if you go very far away from the black hole, you won't feel the gravitational pull of the black hole. And so you have to go very, very close. In order to do that, the resolution of this telescope has to be exquisite. It has to be much, much smaller than the normal telescopes that we have. And it has to be of the order of less than 1/10 of a second of arc. Whereas normally, as light comes through the atmosphere, the stellar images get blurred to about half or 1 arc second or something like that. And that is because light has to come through all these layers of the atmosphere, each of which has a different pressure, temperature, and density. And so the refractive index varies along its line of sight. And as the light comes through and reaches the focal plane of the telescope, you're taking a picture of a long duration. The image of the star will move around very fast because the refractive index is changing in the atmosphere, right? And so things get blurred. Whereas you really need resolutions of less than 1/10 of an arc second in order for us to see the stars that are orbiting the central black hole in the center of the Milky Way from our position, from the Earth. And this is achieved by this amazing thing called adaptive optics, where the mirror itself can change its shape in order to compensate for this effect that the atmosphere is having. This it's a very new technology. This was developed for doing this kind of thing. In fact, here in IUCA, we have an adaptive optics lab where we build adaptive optics for smaller telescopes than the Keck. And these people actually did this. And as you can see, they chose these stars near the center of the Milky Way and made them. So this is what would happen if you take a big telescope like the Keck and image the stars near the black hole. You see, you will have a big blur like this. So you won't be able to pick up the stars individually and find their orbits. On the right is what happens with the Keck telescope using this thing called adaptive optics. You can see that you can pick up the stars. And the second smart thing that these people did was they chose the wavelength of observation to be in the near infrared at 2.2 microns. At this wavelength, light can pass through all that dust. The dust becomes transparent. Actually, blue dust, in the blue light, that dust is completely opaque. And so, you're using infrared observations to make sure you can see through the dust all the way to the center of the galaxy. And B, you actually have this amazing technology such that the shape of the mirror can change so that the resolution becomes exquisitely wonderful. And so these two groups, as you know, got the Nobel Prize this year. Andrea Ghez in UCLA, who used the Keck telescope, and Reinhard Genzel, who from the Max Planck Institute of Astronomy, he's hiding his last letter in his word. Genzel, he used, his group used what is known as the very large telescope. Astronomers have this funny way of naming telescopes, called them very large, extremely large. They'll soon run out of adjectives. So this is called very large telescope, and these are 8.5-meter telescopes, 4 of them that are in Chile, and so in Hawaii and in Chile, 2 sets of telescopes looking at the same object. And they started this amazing work in 1990s, trying to figure out whether you can measure the orbits of these stars. And so, as you must have seen this long ago. I mean, I'll show you a better version of this. This is from the Keck group, and you can see here in the star-marked place is where the black hole is supposed to be in the middle of our galaxy, right? Which you can't see, of course. Now, these are real pictures taken all the way from 1995 up to now, and every night these stars are imaged using these telescopes, and then people have a point where it tells you where that star is. So all these stars, SO2, SO1, SO38, SO37, these are stars that are moving around the central black hole in Sagittarius of the Milky Way. And if you see their orbits, you can see the time here. It shows that week after week, month after month, these stars throw up these amazing orbits. And of course, this amazing star, my favorite, which is SO2 itself, gave this amazing orbit long ago. In fact, it has an orbit of 15 years. And so even when they started monitoring this in 1995, 2000, 2001, they already had a part of the elliptical orbit that could tell you what this black hole is. And you can see that just like normal Kepler's laws, you have the black hole at the focus of the ellipse. And one of the focuses, as you know, everything moving according to a central force, an inverse square force, goes around in an ellipse with the star at the focus. And so here it is at the focus. And you can, from a relativistic version of Kepler's laws, you can actually find the mass. The second thing is, it was also, so here you are, they did this amazing experiment, and as a result, both these groups found these orbits, and you can see from each one of them gives a different estimate of the mass of the black hole in the middle of our galaxy, right? And this is done independently by Reinhard Genzel and Andrea Gheze's group, and this is why both these groups were recognized this year for half the Nobel Prize. Of course, the other half went to Penrose, who did the theoretical work on black holes. And the way you do it is that you take 15.2 years, you fit a Kepler orbit to it, and here is Sagittarius A star, which is the black hole in the middle of our galaxy at one of the focuses. And then you can also see that take S2, which goes so close, it goes almost 10 to the 10 kilometers close to the black hole. And if you work that out, you will find that it's much, much smaller than a light year. And so what happens is that if this was, say, something that has the mass, which was calculated to be 4 times 10 to the 6, so 4 million, 40 lakh times the mass of the sun. So this is a supermassive black hole right in the middle of our galaxy. And if you convert that into its Schwarzschild radius, using the formula I showed you, it's about 15 times the radius of the sun. Our radius of the sun, not if it turns into a black hole, but it's pretty big. And you would find that, and this star is going very close to it. It's 10 to the 10 kilometers to it. Now, if this 10 to the power 6 solar mass object was a star cluster or a collection of stars, it would be several light years across. So it would be so much bigger than this star going around would have collided with it. And so it shows that it's a very compact object, and also shows the mass, and thus proves that this is a black hole. It cannot be anything else. So for doing this, they got the Nobel Prize. This year, of course, is a fantastic achievement, not just doing this calculation, but think of the entire technology of building telescopes with mirrors that give you that kind of resolution, and then building detectors that can actually detect the images of these stars. in the near infrared, as well as then following this, monitoring these stars near the central black hole for 25 years. It's just amazing, simply amazing work that helps us find the supermassive black hole in the middle of the galaxy. So here you are. So the question is then, I told you then, so then this is a supermassive black hole in the middle of our galaxy, and then there are other galaxies in which they have supermassive black holes. You remember a couple of years ago, somebody, the Event Horizon Telescope, imaged the supermassive black hole in the center of another galaxy, M87, and things like that. So those are, I'm not going to talk about that today because I don't have that much time, but I would like to shift my now attention to what happens to stellar mass black holes. So these are million to billion times the mass of the sun, but there are black holes, most black holes that are there in the universe are a few times the mass of the sun. How do you detect them? So I'll talk about a couple of different ways of doing it very quickly. One of the most important ways, and that has been being done for a long time now, in fact, that when I was a student in my PhD days, in fact, I attended quite a lot of classes by Stephen Hawking, and Stephen Hawking had a bet with everybody else in the world that black holes will never be detected. And in the 1980s, when I was a student, this was a big thing. In the 1990s, Stephen Hawking then withdrew and actually conceded defeat, saying, I have lost the bet, because he acknowledged that using X-ray astronomy, people had not only detected stellar mass black holes, but actually had showed and measured their mass. And I'll show you how. So what happens is that most of the stars in a galaxy are in binary systems. They are in going around binary system, two stars going around each other, actually more than 50% of stars. And of course, if you're a planet around them, you see two suns in the sky, like Tatooine in Star Wars. So our solar system is kind of unusual because there is only one star, but you have two stars. Now, if you have two stars in a system, then think of them as, they will of course be unequal. One will be smaller than the other. And in stellar evolution, what happens is that the more massive a star is, the faster it evolves and then ends its life. By what I mean ends its life is that its nuclear reactions in the middle that produces energy finishes. And it uses up its fuel faster if it is more massive. And so more massive stars end their energy generation, and once energy generation finishes, then they go out of equilibrium, and if they're massive enough, they explode, leaving behind a compact object. And this is a standard stellar evolution. People can, when they study astronomy, astrophysics, they learn about this. And if, for example, they are something like our sun, it leaves behind a remnant. It doesn't explode, it leaves behind a remnant, which is often called a white dwarf, which is the size of a planet. The entire star compressed to something the size of a planet. But if it is more massive, like 3 or 4 times the mass of the sun, then it can explode. The outer layers will explode, and the inner layers will implode, will contract and form a very compact object. And these can be neutron stars, which are about a few kilometers across, or it could be black holes. And as you saw, the black holes are less than a few kilometers across, and so it can form a very compact object like a black hole. So, for example, in this system, imagine that the more massive star, which is much bigger than the sun, does that. And it explodes, and the central bit becomes a black hole. This is a black hole, right? So now you have a normal star, which is still happily burning nuclear fuel, and a black hole going around each other, right? And so in its own time, the smaller star will also start evolving, and towards the end of its life, the star becomes very big, and it becomes very red. And as it becomes big, the outer layers, the gravitational pull on the outer layers become very weak. And so it will get to a stage where the black hole, which is the companion of this star, will start pulling the outer layers of this star. this normal star, and they will start falling on the black hole, right? So you can see mass exchange happening within the system of binary stars. And so this mass that falls onto the black hole, interestingly, will have angular momentum, of course, because this star was rotating, so the stuff that's falling onto the black hole has angular momentum. You can't destroy angular momentum. So the mass that goes onto the black hole does not go right in. It forms a disk around the black hole, and this is called an accretion disk. Okay. And for a long time, this matter that's falling onto the black hole will orbit the black hole, and slowly, due to dynamical friction, its orbit is going to get smaller and smaller, and then finally enter the black hole. So this accretion disk that exists around a black hole will remain for a long time, millions to billions of years, and this, because of the extreme gravitational energy of the black hole, is going to get very, very hot. How hot? It turns out it will get 10 to the power 7 degrees hot. And when something is 10 to the power 7 degrees hot, if you use normal black body temperatures, they emit X-rays. So here's an artist's impression of what's going to happen. If you have that black hole here, you don't need to see the black hole. You can see this accretion disk around the black hole, which is so hot, it emits X-rays, right? So these are the stellar mass black holes now, and the accretion disks around them. Now, what are X-rays? You know that electromagnetic radiation has this entire spread, and I was talking about optical and infrared before, which is the middle, which is the kind of radiation that you see with your eyes. But the higher, much higher energy, much higher energy radiation is X-rays. X-rays have wavelengths of nanometers and correspondingly very high energies, right? And so the problem is, how do you find these X-rays? The atmosphere stops these X-rays and ultraviolet rays, things at such high energy, from reaching the Earth. So you can't have a telescope on the surface of the Earth and find these stellar mass black holes which emit X-rays, right? They're not emitting X-rays. The black holes are not emitting X-rays. It's the accretion disk around the black hole that's emitting the X-rays, right? And this is why Stephen Hawking was so confident in the 1980s that we'll never actually see these things. Because A, nothing comes out of a black hole. And secondly, if, for example, they emit X-rays and gamma rays, how are we going to see them? You have to actually make images of these things that are exquisitely high resolution, which will be very much like optical images, right? And you can see in the X-rays, atmosphere is opaque. So you need a space telescope to begin with. And that's where the Chandra X-ray Observatory came. Chandra, of course, is named after Chandrasekhar, who, we didn't talk about this before, but Chandrasekhar was the person who first showed how black holes will form, and worked out the relativistic effects of black holes and things like that. And so when NASA decided to make this amazing imaging telescope which will produce these images of these 10 to the power 7 degree hot accretion disks around black holes, they chose Chandrasekhar's name to be the name of the telescope. And this was launched in 1999, and it's an amazing telescope. I'll tell you a couple of very interesting things about it, just to show how amazing it is. First of all, it has imaging optics. It images X-rays, and I'll tell you in a minute why that is very, very important. But also, it's got these very long orbits. You can see it goes all the way out to 122,000 kilometers, and it's an orbit of 64 hours. The Hubble Space Telescope has an orbit of 90 minutes, and it's a circular orbit near the Earth. If you're imaging X-rays, you cannot do that. You have to go very far away in order to be away from radiation belts that surround the Earth. The Earth, there's a lot of charged particles that come from the sun, and they surround the Earth. These are called the Van Allen belts, and they actually have a lot of high energy phenomena. And to actually make these measurements, you have to go very far away. Chandra does that. We also, as you know, have our own telescope, which is actually near Earth orbit, called Astrosat. ISRO launched this 5 years ago, And Astrosat also has an imaging, a soft X-ray telescope, which is an imaging telescope. And as well as, of course, Astrosat mostly does not imaging, but it does spectroscopy. And as a result, it can have a circular orbit like the HST, but very near the Earth. But it doesn't focus on imaging that much in X-rays, that is. And Astrosat is playing a very, very important role in finding characteristics of the black holes in our galaxy. And I'm very proud of it. So the X-ray mirrors are something that I would like to point out is very, very unusual. You know, what happens is that if you have a mirror in optics, you understand that there is normal incidence and there's reflection and you form an image. You can't do that with an X-ray mirror because the wavelength of an X-ray photon is nanometers. The interatomic spacing on a solid surface or interparticle spacing is of the order of nanometers. So if you have an X-ray photon that impinges on a certain surface, it goes right through. You know that because you take X-ray images, going to the hospital, taking X-ray image of the inside of your body, because X-rays penetrate normal solids. And so you can't really focus X-rays using normal incidence. What you have to do is to take a surface and have X-rays fall at a very small angle. This is called grazing incidence. And when it falls at a small angle, it does not see the interatomic spacing or interparticle spacing as nanometers, but it sees it as a much, much smaller fraction of that. And for example, typically, you have to have X-rays falling on the surface at angles less than about 2 degrees or so. And so you have to build mirrors that are grazing incidence mirrors, and this is why these are very long. And you can see that this is the Chandra mirrors, and they're nested, and X-rays fall on these things, and they are slowly deviated into a focus very long distance away. This is why the Chandra X-ray telescope is 5 meters long. And that's the entire mirror itself is very long. You can see the Astrosat mirrors, the SXT, built in the Tata Institute by Professor K.P. Singh and his group, also does that, and it's built like this. It's just a set of concentric metal foils that actually build this, that makes these images. The Astrosat imaging quality is not, of course, as good as Chandra. It was not built for it. It didn't intend to find black holes. And so the resolution of the image itself is a few arc minutes, but Chandra actually produces images, the only X-ray telescope in the history of X-ray astronomy that has produced images that have the resolution of a quarter of an arc second, almost as good as those Keck telescope observations that I told you about, right? And so what happens here? So you're looking at this also artist's impression of the X-rays that are coming out of the accretion disk around a black hole, and so Chandra was built to find this, and I'll show you what it looks like. So this is the picture of Centaurus A, which is a nearby galaxy that I have studied a lot throughout my career. And in fact, I was associated with this when the Chandra Observatory was built, with the team that built one of the cameras of the observatory. And so as a result, we get a lot of time on Chandra to observe, do our observations. And one of the things that we did was we chose this nearby galaxy. This is a nearby galaxy, very famous. This is, of course, an optical picture taken with a small telescope. And right in the middle, there is a supermassive black hole. Right, and also there are all these stars around. They are normal black holes. They are stellar mass black holes in binary systems. So if you look at this optical picture, you are seeing normal stars, and these stars are a few thousand degrees hot, like our sun, for example. Our sun is 6,000 degrees hot, and it emits mostly light. So these stars are emitting mostly light. Now, if you look at this in Chandra, and here is an observation of about 1 million seconds. This is what you see. Same galaxy, but this is the X-ray image. Everything you see in this picture is 10 to the power 7 degrees hot or more. Everything you see in this picture is 10 to the power 3 or 10 to the power 4 degrees hot, right? And so here is what you see. You see the central supermassive black hole, very hot, and it's emitting a big jet, which is being which thrown out of relativistic particles that are 10 to the power 7 degrees hot. And then all over, you see these X-ray binaries that are emitting X-rays. And many of them are neutron stars, and many of them are black hole binaries. In fact, I had a PhD student who studied every single point object in this picture, and through its spectral analysis, figured out what the nature of the compact object is, which are black holes and which are neutron stars, right? So this is one of the most popular ways of finding black holes. Now, this has now been, of course, so the nearest known black hole that Chandra has found is about 1600 light years away. So please don't be afraid. They are not coming to get you, right? They are there in our galaxy. There are thousands of them, maybe hundreds of thousands of them all over the galaxy. But only recently, and I'll come to the conclusion of my talk by saying something else of how black holes are discovered. And as you know, in the last few years, we've found another very interesting ways of finding black holes, and that's becoming important in India. And here, it is tantalizingly showing us that there are this middle black holes as well. And this comes from the various mega projects that the Indian government is now getting into, as asking us to get involved in. There are all these astronomical mega projects, and this is why we need people like you, the students at this university, who are getting interested in astronomy, because in the next 10, 20 years, we are going to get into some really, really big astronomical projects. And here I'm talking about the top two. The 30-meter telescope will be built in Hawaii. And this is exactly the same as the Keck that you saw. The Keck had 36 mirrors that make up that 8-meter surface, a 10-meter surface. The 30-meter telescope will have 492 mirrors that will make up this surface. It's just the Keck telescope in a much bigger way, and will find a lot more of these stellar orbits around black holes in other galaxies as well. And Andrea Ghez, who got the Nobel Prize this year, is part of that, and we are part of that. In fact, I sit with her in many meetings trying to figure out how to build this telescope. India is 10% partners, along with China, Canada, Japan, and the US, to build this telescope, and this will be about 2034, 2035 by the time this will be built. And this is where people who are undergraduates now at CUTN will be in their astronomical careers when this will be built. And the other thing, of course, as I said, is that we are now finding black holes through gravitational waves. As you know, they were discovered 5 years ago, 2015, and in the discovery paper, there were 40 authors already amongst 1,000 from India, and now that collaboration is growing. You know that Einstein's general relativity, as was mentioned by Professor Seshadri, not only predicted that space-time is bent, it also predicted that as things move in space-time, it will cause ripples in space-time. And as two black holes go around each other, these could be stellar mass black holes, but in a binary system in which both things are black holes, not one normal star and another black hole, but both are black holes, and they're going around each other, or one could be a neutron star and one could be a black hole, and then they merge together, they cause ripples in space-time. That was predicted by Einstein, but Einstein didn't think that they could be actually detected, but this has been done 5 years ago by the two current LIGO observatories, which are gravitational wave observatories. I'm not going to go into the details of how they did it. It's a fantastic technology, of course, and I can come back and tell you later on about the technology. But these two observatories, one in Hanford and one in Livingston, 3,000 kilometers apart, both detected at the same time. In September 2015, the signal of the two black holes merging, and as a result, space-time itself vibrating, and that has now led to, in the last 5 years, some amazing discoveries. This one was the merger of two black holes of about 30 times the mass of the sun, and merging together to form something about 60 times the mass of the sun. Already, this was much, much bigger than the ones that we were finding through Chandra X-rays. But now, in the last a couple of years, we have found evidence of things, at least 3 of them, which are more than 100 times the mass of the sun. In fact, the most massive that has been found is about 145 times the mass of the sun. And this is getting into the interesting regime where we can call them mid-mass black holes. And so each of these events that we find in gravitational waves find 2 black holes, and they merge to form a third black hole. So 3 black holes are detected, and so you can see some of these. And if you look at this particular plot, it's a very, very interesting plot. It shows the mass on the y-axis of the black holes that have been found. And here you can, the purple ones are the ones that are found by electromagnetic waves, like X-rays, Chandra. So you can see the ones that we were finding were 5 to 10 times the mass of the sun, like the ones I showed you in Centaurus A, and many in our galaxy. But LIGO is finding the blue ones, which are much, much more massive. So it just shows there's a totally different technology, and now we are finding a totally different kind of black holes, and we don't know where it's going to go. As the sensitivity increases, we are going to find better and better and more of these, and figure out where it's all going. And this is why it's exciting, because we are building the third LIGO in India. And it's going to come up in Maharashtra, in the Hingoli district. And we've already started building it. We've already started, the land has been bought, and we're going to start building it. And hopefully by 2027, it will be ready, and it will be the third LIGO. And by that time, the technology would have developed such that we will be finding one of these systems every day almost. Right now, it's about 1 or 2 a month. But till now, in the last 5 years, we've found 50 of these events. So I just want to stop there, and I'll ask you to read some of these books if you are very interested. My favorite book is by Kip Thorne, Black Holes and Time Warps. There's quite a lot of interesting books about time travel, etc., related to black holes. And I think everybody should read a good biography of Einstein. I'll stop there. Thank you.
Oh, thank you very much, Seshan, Professor Shumak, for a very simple introduction to something that is really, tough to understand. Thank you very much. It was very, very interesting. Would you have the time to take a few questions?
Yes, of course.
Yeah. So there is one question from the YouTube. I think the lone viewer there, Pani Sarah, who says, who's asking you if the sun goes around the black hole. Does our sun go around a black hole? You're both muted. You're both muted.
Yeah. Our galaxy has this supermassive. Our galaxy has this supermassive black hole in the middle, right? And so a lot of the stars are going around the center of our galaxy. But our sun is not going around the center of our galaxy because of the pull of the black hole. We are very far away. Our sun is just moving in the galaxy, and with a certain speed, it's about 200 kilometers per second, and it is going around the center of the galaxy in an orbit. Yeah, and that's because of the general mass of the galaxy, and the mass of the galaxy inside our orbit is pulling it, right? And the black hole is only a very small portion of that. The black hole is not pulling our sun, and our sun has no black hole anywhere near it. As I said, the nearest black hole we found is about 1,600 light years away, which is very, very far away.
Right. There are quite a few questions from Devika, but the first one is something that I had to. Why are the accretion disks around black holes not spherical in shape?
Well, again, that is to do with, you can ask the same question about our galaxy. Why is it flat? Why is it not spherical in shape? And that is because if there's a significant amount of angular momentum and you have even a spherical cloud, it tends to collapse into a disk-like shape because there is an axis that is defined by the angular momentum. And perpendicular to that axis, it tends to collapse. And so this is why these galaxies also, as these galaxies are rotating very fast, they collapse perpendicular to that axis. And similarly, accretion disks also, because it's formed by matter which is defined by their angular momentum, will have a certain axis defining their angular momentum, and that's why it will be in the form of a disk. And it's not necessarily related to the spin of the black hole, but it's the spin of the swirling mass that's going into the black hole. And that's why it's
There are two questions which are related to viewing sci-fi movies, and hence these questions. One is that do white holes really exist? And the other question was whether time travel via wormholes is possible.
I'll ask Professor Sheshadri to answer these questions or address these questions.
Yeah, as far as white holes are concerned, let me put it this way. The theoretical framework does not forbid it. But I mean, there has not been any observational evidence that such a thing exists. What is the second question? I mean, it is something like this, it is, okay, so I will not go into the details. So basically it says that for every black hole, there is a reverse thing which is possible mathematically. But, the nature does not have any obligation to follow the mathematics which we make. Yeah, what is the second question?
It's about time travel.
Wormholes.
Time, you see, once again, it is the same thing. So you have a mathematical structure which predicts a wormhole. Once again, it is a consistent mathematical result. But anything which is consistent need not be realized in practice. So unless at the end of it, physics and astrophysics is an observational science. One has to remember, no? So unless you finally observe it, you don't have it. Yeah.
So I'd like to add one thing in addition to this. I mean, it's wonderful for science fiction to come up with these ideas, and science fiction job to be imaginative. And science fiction should not actually take ideas that are forbidden by physics, even though they do it all the time. So yes, if it's forbidden by physics, yes. It can be fantasy, but not really science fiction. I call it science fiction if it's at least allowed by science. Now, once you allow something in science, that does not mean that we have the technology to do it, right? So, for example, in principle, time travel is possible. In fact, very interesting features of the nature of space-time. Inside a black hole, actually, time becomes space-like and space becomes time-like. And so you can go back inside the black hole, you can go back and forward in time, but only in one direction in space. And this is why you can't come out of black hole. Similarly, fantastic things happen in these exhaustive phenomena. Now, you know that if you fall into a black hole, a human fall into a black hole, you're not going to survive it, because you're going to be torn into by the extreme tidal force of the black hole, torn into your individual atoms and particles, right? And so doing time travel through a black hole like Star Trek does is very difficult, right? We don't have the technology to do it. At least in the physics we know, we cannot survive such a thing, even though it's wonderful to think of doing this. Now, that doesn't mean that some other time this won't happen. We just don't have the technology or the wherewithal to do it. Maybe somebody can find a way of doing it, who knows? But in our current technology, there's no way we can survive time travel through a black hole.
There are a series of questions on imaging. So the first one is how can we actually see the event horizon as captured by EHT against a glowing accretion disk?
Right. So I didn't talk about that. That's a talk in itself. But what we saw there was that, of course, there's a glowing accretion disk. But the question is, what is it glowing in? See, I told you that the whole thing has a range of electromagnetic radiation coming out, right? Now remember that the event horizon image was taken in millimeter waves, in microwaves. It's radio, very low energy, and much lower energy than light, right? And these are radio images that were put together in an interferometer with which were made telescopes all over the world. And it found certain transitions that are found in the millimeter wave, right? The accretion disk is glowing at what temperatures? 10 to the power 7 degrees, and it's creating X-rays. In the microwaves, accretion disks are not visible, right? If you even think of a black body curve, the peak, if the peak is in the X-rays, by the time that black body curve reaches the microwaves, there's nothing, right? So this is why one could go very close and use microwaves and radio waves to image the stars and the gas that's very close to the black hole. It's really high resolution. Remember, the event horizon image has a micro arc second, 10 micro arc second resolution, 10 to the power minus 5 arc second. I was showing you 1/10 of an arc second resolution images. And so these are very different regimes of space.
So Devika, who had asked the previous question, has another question asking, won't the period of S2 get affected by the nearby stars?
S2, yes. Yeah. So all that is taken into account. Same thing happens in the solar system. For example, you can ask the same question. You take the Earth's orbit and measure the mass of the sun. What about the effects of the other planets on the Earth, right? And you can actually theoretically calculate the effects of the other planets on the orbit of the Earth as well, and find that they are small, but they are quantifiable. And people have done that. And people have, for each orbit, you can find out all the other things, etc. And what they do more than change the estimate of the mass is they can have an effect on the orbit itself. For example, if you have a closed orbit and a Kepler orbit, and you kind of assume that it's the only thing there, and an extra gravitational pull from another star or another planet, in the case of the solar system, can perturb that Kepler orbit and make it precise, for example, or make it not a perfect Kepler orbit and things like that. And in this particular case, if you go and read the original papers by Guess's group and Genzel's group, they do all that. It's fantastic. They do the relativistic calculations of all of these. So I kind of showed you one slide, but there's a lot of mathematics that's gone in there in trying to quantify what the effects will be of various things. Because there are many relativistic effects that they have to take care of. There is, of course, relativistic Doppler shifts and all kinds of things.
Kaviraj is basically a student of chemistry, but he had attended one of our IUCA workshops, I think the first general one, and he's very interested. He's the one who asked the question about the white dwarf. So he has a couple of questions, a series of questions about imaging. How does a blurred image of the black hole optimize to get a clear image? What would be the size of such an image, gigabytes, terabytes, order of magnitude? And how do you take chunks of images from a telescope and then patch them to get the original shape of a black hole? So basically, how do you stitch the images together?
Right. So I don't want to get into that because this is to do with the Event Horizon Telescope image again, and I didn't talk about it today. That is a talk in itself. But the things that I talked about was not interferometry. In fact, the imaging that I showed of the accretion disks around black holes in X-ray binaries, those come from single X-ray observations, and those don't even get into gigabytes. They're into hundreds of megabytes or something like that. Those don't have so much information in them. Now, if you take an optical image, normal optical image of these stars that you're talking about in the Keck telescope, those orbits, those single images are probably a few megabytes. But then you're taking thousands of them over 25 years to find out these orbits itself. So so these are not that spectacular. What is spectacular is radio astronomy, which I didn't talk about today. Radio astronomy, what you do is you actually get the data in a much more complicated form. Because in radio astronomy, if you just take a radio image, and if you take the resolution of the image is lambda over d, you'll find that lambda is very big and d is very normal. And so the resolution of a single radio image or microwave image or millimeter wave image is very bad. Yeah, the best radio telescopes, a single dish image, is of the order of degrees. Whereas I'm talking of a micro arc second image. And so that comes from the fact that in radio astronomy it is possible to combine telescopes together and form an image such that the size of the telescope, the effective size of the telescope, is actually the distance between the farthest telescopes in that array. And this is why you have one telescope in Antarctica, one in Japan, one in Europe, and you're building a telescope the size of the Earth. And this is why what you have to do, and this is possible because it is radio waves and the wavelength is very large, it is not possible yet with optical waves or X-rays, is that you can record these observations on a single telescope for a long time, and then bring these observations together and try to find a way of finding an interference between these observations if you have a very accurate timestamp. And this is what was done with the Event Horizon Telescope. Now, to do that, this is why you read a lot about the sizes, because each of these observations were terabytes, hundreds of terabytes maybe, and together they made an amazing, a few tens of terabytes together. These, because these are radio telescope observations, they observe much more than just an image. They observe at every point as a whole spectrum and things like that, and polarizations and things like that. And then you need long observations, and they record everything, and they were brought together. They had to be brought together in tapes, and you've seen pictures of all that. But if you want to know about that, there's quite a lot of resources on the web where you can go and read about the Event Horizon Telescope and the amount of data that it actually used.
So you have to tell me where I stop, because there are quite a few questions, and we can always email them to you to get answers.
Yes, later on. I mean, maybe we can, another 5-10 minutes. I don't know what Sheshadri wants. I mean, there are.
Yeah. So one other question is, do black holes lose their energy due to Hawking radiation?
Yeah, this is one for Sheshadri.
Okay, once again, what is the origin of Hawking radiation? Hawking radiation comes up in a theory where you try to quantize gravity. See, we have a quantum theory of matter. We have a quantum theory of electromagnetic field, but we still do not have a full self-consistent quantum theory of gravity. Now, there were some suggestions about the shape of such a theory, and for which Hawking was quite famous for. And in this theory, there is a radiation which will be coming from the black hole. Now, suppose this theory is correct and nature indeed follows it, then yes, black holes will lose energy. In a very heuristic or a hand-waving way, you can say the following. Suppose you have a box and some particles in it. Classically, things cannot come out, but quantum mechanically, they can do a quantum tunneling and come out. It is something of this kind by which the radiation come out. And now there is one more thing. When you do calculation, you find the center of this radiation is proportional to 1 by mass to the some power of mass, which means larger the mass, lower the temperature. So as initially a large mass black hole will evaporate very slowly, as the mass decreases, temperature increases and the speed of evaporation increases even further. So it is like a runaway process in which it suddenly comes to a halt when everything evaporates. That is what it is. That is what one believes will happen. But as I said, it is a theoretical prediction. But in fact, it is more than just, there are some things in which the theory is complete and the observations are not done. Here, even the theory is not in a completely watertight situation.
I have one thing to add, and it's an absolutely fantastic explanation of Hawking radiation. One thing to add is that if you just work out the amount of radiation that a black hole would emit, Hawking radiation, you find it's very, very difficult to detect it, because for a black hole of the mass of the sun to completely evaporate by Hawking radiation, apparently it will take, I think I did the calculations, sometimes 10 to the power 60 years or something like that, 60.
Oh.
And it's only 10 to the power the whole the universe, right? So you can see by appreciable reducing mass of a black hole due to Hawking radiation is very, 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 very slow. And in the age of the universe, it's not possible. So that does not mean we can't detect. There are ways of finding massive enough black holes, stuff like that.
We have the last 3 questions, so I'll quickly go through all 3 because those are.
Can I ask whether towards the end we can unmute, not unmute, but turn on the videos of everybody? We take a group picture.
We'll do that.
It's beautiful.
We'll definitely do that. The next question is from Alan Sunny, who asks he says, we know that an object in constant acceleration over a long time reaches the speed of light. So can an object falling under a strong gravity of a black hole also reach the speed of light?
Yes.
Okay.
That's the whole, Go ahead. Yes.
Yeah. So first of all, yes, right. Like when you do a constant acceleration, you reach the speed of light. But one has to be a bit careful with that, because how do you reach a constant acceleration? By providing a constant force. But if you keep providing a constant force, what you are doing is to increase the momentum. And when the speed approaches the speed of light, more and more energy which you have pumped in goes into increasing the mass in the kinetic energy. Okay, so that is how there is an upper bound which is reached. Now, as far as when an object falling into the black hole is concerned, yes, it is right that it will reach speed of light when it is approaching the event horizon. But there is one thing which one has to remember. See, how do you detect it? You detect it by signals coming from it. What happens is when an object goes closer and closer to the event horizon, the time interval between the pulses which it sends keeps getting more and more dilated. It takes more and more time duration, such that the interval tends to infinity when it reaches the event horizon. So yes, in principle, it can reach the speed of light. Yes, but the question is, an external observer, can one in practice observe it happening, is a different question.
Okay. Thanks. And here is Atesham Hanifi, and they say that I am from Life Sciences Department. I am purely from a biological field. My question is, how can I make my understanding easy in this subject, because I love astronomy since childhood?
The thing is, as the Vice Chancellor...
Sir, this is my question.
Sorry. Can you hear me?
Yes, sir.
Yeah,
sir, this is my question.
Yes. It's a wonderful question. And I think what we tried to, as the Vice Chancellor at the beginning said, astronomy is a very, very interdisciplinary subject. And it is, because, people ask me, do I have to do physics or chemistry or something like that? And if you look at people who do astronomy, we have people coming from all fields possible. And this is why there are various parts, because astronomy is essentially a detective story. What you do is you arrive at a murder scene and you're seeing very, very washed away clues which are not even perfect, because we can't go and touch those things out there, right? We are seeing them from very far away. We can't even change the experiment. And we are depending on very, very faint clues to figure out what's happening out there. So we have to draw expertise from everything. So if you look at Ayuka in my institute, the faculty and the people who come here, you will find that there are engineers of all kinds, there are computer scientists, there are mathematicians, there are physicists, and now increasingly we have chemists and biologists coming into the field, because we need those as well, because we are finding all kinds of interstellar molecules that require chemistry knowledge. There are biological molecules that are being found in the interstellar dust, etc., etc. And we have the new subject called astrobiology, which is about what will happen if we find life on other planets. What are their life signatures in the atmospheric spectra that have been taken around planets, around other stars? They have fantastic spectra that people are taking now. In fact, ISRO is building a satellite that will totally concentrate on getting spectra of the atmosphere of extrasolar planets, right? And this leads to biological modeling to try to figure out the signatures that you're finding in the spectra, whether they are related to biology or not. And that's only one aspect of biology. So we have astrostatistics, we have astrochemistry, we have astrobiology, we have astroengineering, we have everything. These are, we're looking at all these interfaces of subjects. So eventually you will find, and of course Carl Sagan started this whole thing about involving biologists right from the 1970s, 1960s in trying to figure out the characteristics of life elsewhere in the universe and things like that. So even if you are just interested in astronomy, that's fine. You learn some of the basic tools of astronomy and learn about the subject. But in the end, you might find that the biology you are learning might actually even be useful in the study of astronomy.
That's right. So thank you. I think we'll take the last question, and any other questions, I'll email them to you. Can a black hole collapse on its own? Rashi asks.
On its own.
And before you answer, can I request all the participants to please switch on their cameras so that...
Ishadri, do you want to answer that question? Can a black hole further collapse on its own?
You see, the point is black hole is something to the limit. It is something like, can an object shrink beyond a zero size? So, the size of a black hole, which is event horizon, is something like a zero in, usually in Newtonian gravity. The problem happens at r equal to 0, the singularity. Whereas in the case of black hole, it actually happens, whatever observation you make, it happens at the event horizon. So, it is like the ultimate collapse which can happen.
It's very difficult to further collapse a black hole.
Yeah.
Okay.
Yes.
I'm just waiting for, yeah, please.
So black hole size changes if its mass changes. Now, if you add to the mass of the black hole its size, the size that you find, the size of the event horizon, actually only increases, right? If you manage to take away matter from a black hole, you can make it shrink. But that's difficult, isn't it? Because that's the whole definition of a black hole. So that's it.
No, I'll put it this way. See, suppose you have a star, a neutron star. Then you have something called the surface of the star. Now, the surface of the star is also the surface which you are probing. Now, if suppose you were to have a situation where you can probe only certain height above the neutron star surface, then it doesn't make any sense to talk about what is happening below it. Now, in the case of black hole, the black hole actually goes to 0, although you are prevented from probing it beyond event horizon. So you can't probe it beyond event horizon, you see? So it is not the size of the black hole, it is the size to which you can probe a black hole, the event horizon.
Thank you very much. I mean, I really have no words to thank both of you for spending so much time with us, and answering all the questions. There's just one more question right now, which is like, what is the source of relativistic jets? If you would like to answer, but I request everyone to please switch on your cameras. We would like to take a few screenshots.
The relativistic jets essentially come from it's interesting. So a black hole has a limit to which it can eat as things fall in. It's called the Eddington limit. You work out in astronomy class. And it's to do with the fact that as things fall in, it also releases a lot of energy, gravitational potential energy, and that prevents further falling in. And so there's a limit. So when a black hole is pulling in a lot of stuff and it's falling in and it has nowhere else to go because the black hole's limit has been reached, then what happens? What happens to me when I eat too much? I vomit. So the black hole vomits. The difference is when I vomit things that are coming from inside me. There's nothing inside the black hole, right? I mean, they can't come out. So stuff that's trying to come in, but the black hole can't take them in, is chucked out, is in the form of these jets. And they have so much energy that they attain relativistic speeds, very close to the speed of light. These are essentially the origin of relativistic jets.
Thank you very much. And I have taken the screenshots for whoever was able to switch on their cameras. Thank you. And now I would request Sampurna to propose a formal vote of thanks. But before I do that, I add my sincere thanks to both Sesha and to Professor Shomak for spending so much time and being an inspiration to our students out there. Thank you. Sampurna.
My pleasure.
Absolutely pleasure.
Sampurna?
Can you hear me now?
Yes.
Yeah. So first of all, I would like to thank our students whose enthusiasm has led to the Astronomy Club in our department. Otherwise, like this meeting would not have been possible. And I also express my thank to Professor Somak Rai Chaudhary and Sesh for taking time out from their busy schedule to join us today. And I'm also thankful to them for the wonderful talk and the vibrant conversation that we had just now. It was indeed an interesting talk and a motivating one. I also thank our officiating Vice Chancellor, Professor Kumaravel, for his support by joining us on the inaugural event and giving a motivating introductory remarks. I wish to thank our head, Professor Kavita, for her support in establishing Astro Club in the department. I also wish to thank our colleagues for extending their support. I express my special thank to Professor Madhurima for her ideas, efforts, and constant motivation to keep the enthusiasm of the students intact. I thank all the astro enthusiasts for joining today and making this event a success. I thank all who have helped directly or indirectly in coming up with this idea. And I apologize if I have unknowingly forgot to acknowledge someone who has made this thing possible. I hope this enthusiasm will continue and no drag force will be able to damp this enthusiasm. So I thank all of you for joining us
and
today.
If I might add, we are looking forward to a constant support from Ayuka for the thank you.
Absolutely. We will spare no resources. Don't worry.
Thanks
Thank
a
you
lot.
very much. Bye.